So now I want to introduce a little bit of systematic notation and talk more about pricing by dynamic hedging. How do you get prices for gambles? Alright. So we're going to do perfect information games. With 2 players. And they're going to be called Skeptic. That's typically us, because he's the hero that tries to achieve something. And there is World, in which we put all the things that we don't have under our control. And if necessary, we're happy to split these players into more roles. And the typical split will be that the world has 2 parts, or 2 roles, namely the part of the forecaster, and there the role is to quote the prices and reality, and that role is to generate the outcomes. Okay, so we have these 2 players, Skeptic and World, and we have to specify how they interact. That's called the protocol. And the protocols will be very similar every time, but depending on exactly what statement we are looking at, they vary a little bit. So let me write down sort of the simplest one and a very general one. So the simplest one is called the fair coin game. In the fair coin game, we have no forecaster, because the model is that the coin is fair. So we're going to look at Skeptic betting on outcomes under fair coin prices, and we're going to look how rich does he get. So let's say that he starts out with 1 unit of money, and then we're going to look at a bunch of rounds. Let's go in. Okay. In each round, Skeptic can choose how many tickets he buys. It's a real number. So we'll see what these tickets do in a second. Then reality, so that's the other player. Gets to choose the outcome. Let's call it xn. And let's make it between -1 and +1. Binary. So this is one way of encoding the outcomes of a coin. That's sort of convenient. And then we're going to say what the gambles really do. So the idea is that Skeptic, by this choice of MN, can, in a sense, test whether this coin is fair. So he's able to take a gamble that has a different payoff depending on whether the outcome is plus or minus. This is a very local gamble. And the way we set it up is that if it's +1 and he buys 1 ticket, it gives him +1. If he buys 1 ticket and it's -1, he loses 1. So that way his capital will evolve to be what it was, plus the number of tickets that he purchased times the outcome of this round. Alright, so this is the simplest game that we'll consider. There is no forecaster, the prices are fixed. It's the fair coin model, which means that for going up or down in a fair coin that's even, so the tickets are zero price, if you want.
Sorry, I'm confused. So
Yes.
the word can choose any value +1 or -1, right?
Yes.
So where does the fairness come from? I mean, it's not that it's easy.
That's right. So you don't really see it because the forecaster is gone, but the evolution here of the capital is that the price, so the payoff is for 0 you get +1 or -1, which is a completely symmetric payoff in +1 -1. So yeah, that's in the end where the fairness is hidden. The fact that the tickets that pay +1 -1 cost 0. So they cost 0 because we don't pay anything related to the number of tickets we buy. And that is a fair price if the coin is fair. Because then the expectation is 0 and that is the price that we charge here.
So what happens if the player chooses to pay 0 all the time?
In reality, if the skeptic,
The skeptic, sorry.
yeah, if he always buys 0 tickets, then he keeps his initial 1 and it never changes. And reality can do whatever. So we haven't really defined the winning condition, but you'll see that at that point skeptic loses. Because reality can misbehave and not look at all like a fair coin's outcomes, and skeptic didn't detect it and get rich. Now you have to specify when you win. Good. So I'd like to write down another one, but it's a little bit uncomfortable with this board. Okay. So let's also write down a very generic protocol on an outcome space X. But very similar, we start with capital 1. We do rounds 1, 2, etc. Now there is a forecaster. A forecaster offers us gambles. What are gambles? They are payoffs that depend on the next outcome. Okay? So let's say he gives us a set Gn of gambles that are functions from the next outcome to the reals. Is this okay, this notation? There can be a big set. We'll make some assumptions on it later. It can be, in this case, there was just one, or there was the gambles were in a sense parameterized by Mn. But you can have a complicated set, multi-parameters, whatever. You can have this. Skeptic picks 1. I'm going to take this gamble. Because we always assume that the gambles have a certain closeness property. It doesn't matter that we can pick just one. If we were thinking of sort of hedging several, that will also be a gamble that we already got offered. So we can just pick one. And then the capital evolution is, we still need the outcome. The reality picks xn, and the capital evolves to be what it was, plus the gamble evaluated at xn. So this will cover the protocols that we'll be looking at all the way through the course. So the assumptions will be in what gambles we have. And the corresponding interesting thing is the winning strategy that I still haven't put out. So far so good? Okay. So now I'm going to throw a series of definitions at you. By the way, this document is on the web, so if you want to have it later, then. But it's always good to just write along, I guess. I do that. So the first thing that we'll say is, to make things easy, is that skeptic and world alternate. We have two players, and it's just so much more convenient if they move alternatingly. That's not quite obvious because, especially here, you have forecaster, which is from world, and skeptic, then reality. The skeptic is sandwiched between the two of them. But the way we'll think of it is that we'll just group the reality with the next move by forecaster, and then they can alternate, right? So we have forecaster, then skeptic, reality, forecaster, skeptic, reality, and we'll group them like this, and this is always world. Alright, now let's talk about pricing in a protocol like this. It's funny, but you can define almost everything without a winning condition, and regardless of exactly in which protocol you are. So, path, definition, a path is a complete sequence of moves by world. So it tells you exactly what world did, and skeptic is not there. Okay. And the sample space we call it omega is the set of all paths. So the reason we do it like this, that in the end, we are concerned about whether the forecasts match the outcomes. So we only need world just that, and we think of skeptic as being an external agent that gambles on everything, but he's not needed to test, to judge whether the forecast makes sense. I mean, he's testing it, but we can define whether they do just from the moves of world. So we'll always be thinking about what world did. Okay? So a finite prefix of a path is called a situation. And all situations, we group them together and call it omega diamond. And that's not a sentence. It's a set of all situations. Okay. This is a situation.
Situation.
So a situation is a point sort of in the middle of the game. We're not done yet. We have a specification of everything that the world did in the past. This will be a point where we have to make a choice in the game. Okay. So there is a special situation, namely the empty prefix, which is a prefix of anything, and we call it box. So box is always there. That's the empty sequence. And that's also, if you think of it, the starting state of the game. Okay. So if you took a descriptive set theory course, does that apply to anyone? Tom did. So they call sets like this trees. So they're closed under taking prefixes, and they're finite sequences. So we'll use the same concept, except the descriptive set theory doesn't really matter for us. But we'll think of the set of situations as a tree. Right? Every situation has a unique one shorter one, that's its parent, and all the extensions that are in omega diamond, those are the children of the particular node that you're in, situation. Right, so now it starts to look like a game tree. Okay, so we have a few different types of trees. We have a finite horizon, which means that the path length is bounded. Have you seen that before? There is sort of a maximum length and there is no path longer than that. So then a game is definitely finite. And that's easy if you want to do computation. There's another one which is called terminating, which means that paths are finite. There is no specific maximal length, but still, no matter where you go, you always stop somewhere. And there is infinite horizon, which means that all paths are infinite. So the first, in the next lecture, we'll look at infinite horizon, because it's the nicest scenario to think of when you want to say sort of long-term averages over infinite lengths. They are just continuous. And then in the next week, we'll look at finite horizon. We will fix some length, and we'll look at what can you say in this finite game. All right? Now, a subset of the sample space is an event. So you'll see that we're now sort of stealing words from the measure theory crowd. But in every case so far, I sort of tend to agree that they mean the same thing. So it's not confusing, it's actually useful. We're talking about the same thing.
What? I'm a little confused about the difference between omega and omega diamond now.
Okay, I need to make just a picture.
Well, I think I understand what they are, but so I thought omega diamond was about finite prefixes of paths. So how then does like having an infinite horizon game apply apply to omega diamond?
Yeah, it's funny, but you can tell from omega diamond whether there are infinite paths or not.
Oh, I see. Okay.
The pictures are not so. So
Just draw an infinite tree and I'll understand.
if in omega diamond you can always sort of make the sequence longer,
Okay, I see.
then there is an infinite path. The way to make it terminating but not infinite horizon is typically this thing. So you make a path of length 1, 2, 3, etc., but there is no path of infinite length. So this is infinite horizon terminating. And so the picture is that omega, the sample space, is really about the end. What happens when the game is over. Omega diamond is about what happens before the end. But in the finite case, the end will be included. In the infinite case, it's sort of nicer to leave it out. I actually struggled with this because sort of you both, whether the end is in or not, in the infinite case, both things don't make sense. So they have to pick one. It will bite you somewhere. But the good picture is that, well, let's lie and let's say omega diamond is about everything but the end, and omega is about the fully completed games. And it's not quite right because for the finite ones, omega diamond is also the end. But for example, if you want to talk about strategies, you don't have a move at the terminating node. You only have moves before. So then you'd like to define things only on the shorter ones. This clashes at some point. But I followed it in the end. I thought I was smarter for a while, and then I decided no, it just moves the problem. I follow how they do it. Okay. Almost done with the definitions, and then we can have a break. So, a variable, so now we're being very careful. A function from the sample space to the reals is called a variable. So, probability theory people would call this a random variable. They say that's confusing. It brings in all these connotations of sampling and just randomness at large. So they have the same notion, but they call it just a variable. So it's a function whose value you can figure out when the game is over. And we have a similar thing. Okay. From situations. And that's called a process. We're going to use these words like crazy all the time, so it's good to get used to them. Let's say one more thing.
So the process is like an output.
No, it's not. Yeah, yes. Sorry, I was predictable, but that's right. This is also what so in measure theory you have these filtrations and then you have process, but we will not worry about them. Maybe you should ask me later about why we don't worry about them. Okay, so a variable, for example, would be the value at the end, and a process typically is, for example, a strategy. Right? A strategy needs to choose, for example, over here, this number of tickets that you buy. You want to have a way to do that in every situation, so you need to come up with a process to build this strategy. Okay, let's do one more, and then So if you have a process, you can turn it into a variable. Because a process, you know it at a certain, well, let's say it differently. A process is defined everywhere. But if you look at a certain round n, then you can see what is the process value at this point. And you can make a variable that has that value. So that variable we're going to denote by, so we have a process, let's call it S. I'm using many letters for process, I'm not standardized, I'm following the book. So we're going to define Sn, which is a variable, so it will be evaluated at the path where I have to write xi. So I have to put a number at the end along a path xi, and we have a process S, so we're going to use S and ask what do you think after n rounds, right? Where this restriction to length n is really just the first n elements of this slide. So now we have a nice notation to talk about the process value at the sequence of time indices. Let's have a break. Let's start at 1:15. I still have a few more things to add, but it doesn't matter. We can crunch a little bit on the history. There is a coffee machine in the hallway with tea and